We're pretty used to taking derivatives of functions, and that's a good thing because in a lot of artificial intelligence and machine learning applications, such as deep learning, require something called gradient descent, and in that process, we need to compute derivatives. Now, we know we can do derivatives pretty quickly, but symbolically, the computations of derivatives can, in certain instances, get pretty complex. And more so, the derivatives just get really arithmetically large, and it's highly inefficient to take derivatives in that respect. So let's say here we want to take the derivative of a single function. Notice we don't have a vector over it. A single function with respect to a vector of inputs. In this case, those two inputs are x and y. So what we want to come up with is we want to come up with this small vector, which will have in it the derivative of f with respect to x and the partial of f with respect to y. Okay, so we can compute these two derivatives in three main ways. One of those is just to do derivative. And of course, we can do that, but notice that it's going to require some chains and chain rules. So if you would do this through the standard differentiation rules and you wanted to compute the partial of f with respect to x, first of all, you would have to take the derivative of what we would kind of think of as natural log of this stuff. Well, the log is 1 over the stuff, which in this case is the 4x squared plus 3xy. If this were just natural log of x, its derivative would be 1 over x. But now we need to multiply it by the derivative of the inside. So the derivative of the inside, 4x squared, would give us 8x, and 3xy, its derivative would be, with respect to x, would be 3y. And so we would end up with 8x plus 3y over 4x squared plus 3xy. Now, this is just the partial of f with respect to x. We would repeat a similar type of process for the derivative of f with respect to y. And as you can see, this is a relatively harmless looking function, and its derivative is already kind of getting pretty large. It's much easier for certain functions to just sort of do it symbolically, but like I said, this can quickly get pretty messy. So we want to try to avoid that, and we want to avoid the computational inefficiencies that come with it. The other thing we could do is we could numerically compute the derivative. And numerical is where if all we're looking for is a value, then we can just come up with a number for the derivative. But we can use the more rigorous definition of a derivative. Well, what does it mean when you have two variables in it? Well, in Calculus 1, you might have learned that just omit the y part, right? F of x plus h minus f of x over h. The idea was that here you have some sort of function, here you have some x value that you want to compute the derivative at, but then you have this other point over here, this other value of x, which is h units greater than x. And so what you would do is ideally you would take these 2 points and you would make the distance between them as infinitesimally possible as you can. In other words, you want to move this point in the leftward direction. You want to minimize, make as close to 0 this distance h. We're not going to do this here, but you could calculate this numerically, but the problem is you get rounding error, and it can become a really big problem. The third and most likely new way that we'll see this in is what we call automatic differentiation. Now, the automatic differentiation is, it's kind of a misnomer in a way. I mean, it's not automatic, but it automates the process. So in that sense, it's automatic. But it's not automatic as in it's instant or in sort of what we might imagine. So the way automatic differentiation works is that we use the chain rule to really deconstruct the function. And we can sort of imagine how we're going to break these chunks up by using what's called a computational graph to represent the chain of steps. Now, ideally, these chunks are simple arithmetic operations. So, for example, taking a log. That would be one arithmetic operation. Addition would be one arithmetic operation. Subtraction, multiplication, division, sign, all of these things can be thought of as a simple arithmetic operation, maybe not even arithmetic, simple operation, I'll just say. And if we can break it down to this level, then we really only need some of the basic derivative rules. And there's two types of automatic differentiation. One is what we call forward, and one is what we call backward. Or rather, I should call it reverse mode. And then forward mode. Now, these are sometimes referred to as modes of what we call automatic differentiation. Some people will call this autodiff for short. And the idea here is, well, we're mainly going to focus on the reverse mode. The forward mode, we're going to draw this computational graph, and we'll see with the forward mode, we have to do one derivative at a time. So forward mode, we'll do one partial at a time. Whereas when you do reverse, you'll do both at the same time. And it all just matters whether you follow the computational graph from left to right or right to left. Left to right would be forward mode, right to left would be reverse mode. So for our function, which we had up here, natural log of 4x squared plus 3xy, we would want to break this up into as many miniature expressions as we could. So let's just start with over here with our inputs. So we have x and y. And there are lots of ways to draw this, but what we notice first that happens to x in this first term, and we're focusing on the innards of this function because that's, think about composition of functions. It's a natural log function composed of a quadratic and this interaction term. So the first thing that happens to x for this left term is it gets squared. So I'm going to draw an arrow and over to this box, and all this is going to do is it's going to take that element and square it. So I'm going to use that as a dot, right? You could put x in there, but the idea is that whatever comes in there gets squared. Then for that other term, the 3xy, the first thing that's going to happen there is you're going to have a product of x and y. So we're going to have a multiplication of the two inputs. And so maybe I'll just draw off a branch like this, and then y also comes in there. They get multiplied together. The next thing that happens to the square of x is that it will get multiplied by 4. Will get multiplied by 4 times that value. And down here, what the next thing that happens to x times y is it gets multiplied by 3. I'll just omit the multiplication sign here for ease of the notation. Okay, then what happens is these two quantities get added together. So they feed into this next computation, and this next computation will be the sum of those two values that come in. And finally, whatever comes out of here, we're going to take the natural log of it, and that's going to give us our output, which we'll call z. All right, well, what's happening here is if you notice at each of these junctions, at each of these phases, we are performing one simple operation. So you can see here, there's a multiplication. Here, there's, again, a multiplication value times itself. Here is multiplication, addition coming into here, and the natural log. So we've broken this up into manageable chunks that make this much easier to follow. So let's say we gave this a couple of values. Let's say we gave it an input of 2 and 1, just so we could see how this tracks. So if x is assigned the value of 2 and y is assigned the value of 1, then this will still compute the output of the natural log of 4x squared plus 3xy. It'll just do it in pieces. So here the value gets squared, so a 4 will come out. And then it gets multiplied by 4, so 16 will come out here. Down on this bottom chain, we'll have a 2 and a 1 entering, so that'll give us 2 times 1, which is 2. Then it'll get tripled, give us 6. These two values will get added together. That will give us 22. And now we just need the natural log of 22, which comes out to about 3.09. And so there is our output of 3.09. Now the one thing that we can do here is we can label all of these quantities using different values, right? So we could say that what comes out of here, we'll refer to this as, say, A, and we'll refer to this as, say, B. Then what comes out of here, we'll call maybe C and D. And then what happens here, I won't use E just to not confuse it with Euler's, but with the Euler's constant E for exponential. And then what comes out of here will be G. Now what we've computed here, this 3.09, notice that that is our function evaluated at an x value of 2 and a y value of 1. Gives us that output of 3.09. Or approximately, we should say. This is what we call, for the reverse mode, we're doing the reverse mode, but we're doing what's called a forward in the reverse mode. So the reverse mode actually consists of two processes. There's the forward pass, and then there will be the reverse pass. We're going to take a look at the reverse pass in the next video. What we should also point out here is if you're wondering, well, what's the connection between Z and G? It should be noted that and G are the same thing. And so you might be wondering, well, why don't we just say Z is the natural log of F? And the reason is because we may have multiple outputs for this function, and maybe Z1 is one of them, but then G also gets fed into perhaps another series of computations to compute a different output. And so that's why we want to distinguish between Z and G, is because in certain cases, outputs may not always be the terminal point for every single function within our vector.